everybody. Thank you very much for having us at Activate. My name is Eugene Steinberg. I'm VP Technology at Grid Dynamics, and I'm working in the digital commerce space and search space for about 12 years. And with me, I have Stolpovskiy. Stas?
Hello, everyone. My name is Stanislav Stolpovskiy. I'm working in Dynamics for the last 11 years. Working with search and machine learning. Be happy to present you today.
Right. Okay, so let's take it away. Today we are going to talk about neural search in digital commerce. And just as a quick recap, the motivation behind implementation of neural search in digital commerce lies from the observations of the typical query frequency diagram in digital commerce, which usually shows that the head queries are relatively simple. They represent name, title, brand, or combination of the simple attributes, and the traditional search techniques such as concept search or semantic query parsing are very effective in tackling this kind of queries. However, as we go down the slope of the frequency, we go into the torso queries and long tail queries, which are typically much more complicated, and they are much harder to attack with the knowledge graphs or traditional kind of concept search techniques. This is where neural search and basically machine learning based search becomes extremely popular and effective, neural search retrieval. And we are going to talk today about neural search specifically. We will talk about what is new happening in the space of neural search, and most importantly, when you implemented your first neural search service, how to implement it in a non-disruptive way into a working search ecosystem. And just as a quick recap of the main ideas of the neural search, the idea is to encode products and queries as the semantic vectors, which represent the similarities between the products and similarities between the queries, and then to be able to match vectors with each other, and this way to retrieve the relevant products for a given query. And the whole system is trained on the behavioral data to achieve this semantic encoding of a vector. So the majority of complexity lies in this query and product encoder piece. And one of the architecture which we represented on the last Activate is the so-called DSSM architecture, which is shows a pretty good practical results trained on the using triplet loss with hard negative mining, and takes a variety of input, including the product queries, product text, n-grams, image features, and many other types of the data which is available for the products. However, today there are many other interesting neural search techniques, and Stas, please take it away and talk about them.
Thank you, Eugene. So let's try to see what was the main researches for the last years, which affects the neural search. And I want to start with, I think, one of the most important papers that was published and the model that was available, which is a CLIP. CLIP is an OpenAI project. It's one of the first successful models who can incorporate two types of information, text and images. And this model was able to provide very good description for the images, and it was able to retrieve, using this model in the textual description, we was able to retrieve the images that match the description. That's have a huge effect on the neural search, especially for e-commerce, when you have only product image and lack of description for it, and you need to connect user search queries with these products. So using this model, you now finally have ability to do this. And it's open for us the whole new window of opportunities to provide the searches for the abstract or for the thematic types of queries. So as example, we experimented a little bit with this, and we was able to match patterns without any textual descriptions using only text query and the clip model. And we was able to match very efficiently these patterns. And we also was able to get results for very abstract queries that represent some kind of idea or the theme or like just a number of the colors. And we are able to match the products that looks like this idea. So this opens us a lot of new opportunities to do the matches which we wasn't able to do previously. The second important thing I want to mention today is the evolution of the Colbert model. Colbert is an evolution of dense retrieval model, which all started from DSSM model, quickly became a more sophisticated approach. And in Colbert, we have not a single vector for the document and the query. We have multiple vectors for the document and the query, which have late interaction between each other in the late phase when you have a query and the products. Previously, it was working, it already was showing great results, but we have a huge computation cost for this and a huge index. And the recent research helps to decrease the inference time up to 7 times. And it's bring this model into the scale of industrial ready standards. It still requires a huge index, but it's something that we can deal with, and we can show good results in a reasonable time. And the last research I want to mention today, which we was able to use in our search systems, was SPLAID. SPLAID is a model that help to predict the term importance on the good old bag of words index. Bag of words have the binary intersection between the query and the terms in index. You have intersection between terms, or you don't have intersection between terms. Now, using SPLAID, we can have weighted intersection, and we can include terms that doesn't have direct match by text, but still can have relevant context and can be included in the results. That's help to solve out of the dictionary match problems, which was previously can be solved only using dense retrieval. It's not solving it the same way, because you can have index without any terms even close to this, and dense retrieval can work with this, but SPLAID cannot. But it still helps to improve relevancy a lot. So let's talk about how we can use all these models together in the single neural search application. We have a search request coming from the customer and sent to our search API. And our search API fires 3 parallel calls to our models, each model using its own index to produce results. In case of the Splat, we're using Solar Concept Index, and we apply model on top of the results that we're getting from this contract index. In case of the clip and dense retrieval, Colbert-like models, we need to encode the query first and then do matching with existing product index. And then when we have results from all these 3 approaches, we send all these results into Result Blender. Result Blender is a system that help us to create the final result set, which we will be returning to user based on the 3 result set that we have in intermediate retrieval stage. And when we do this blending, we have 3 main strategies which we can use to do blend. First of all, and the easiest one, we can do fallback. Fallback means that if you don't have results from your term index, which you're using right now, in most cases, then you can do a simple fallback to the system of neural search. It can be clip-based model, or it can be dense retrieval model, or even combination of them. The pros of this approach is that it's simple, it's safe, not compromising any existing relevancy, but the comes from the same concept that you're not improving any of your existing relevancy issues. The backfill helps systems when you don't have enough recall, and you can backfill results, low recall results from neural search systems. It's a semi-efficient approach. Sometimes you can backfill with good relevancy, but if your system returns bad results at the beginning, they still will be shown at the beginning. So it's not solving all problems, but it still helps if your system hurts from low recall. And the most effective and the most complex approach is to blend results, incorporate all these three systems. And that works perfectly to fix relevancy issues, but it will require some tuning, and it will not be working on the cold start. Let's talk about this blending more deeply. The basic approach that we introduce here is that each of the retrieval systems have its own weight. And when we do final score calculation, we take weights for the product from each system, and we apply coefficient for this system, and we get the final score. So in this case, you can have each system being tuned based on this efficiency. And more important, that you can apply these numbers not only for the overall recall, but even for the category level. It means that if you see that in the core category, the clip model show you the best results, then you can set higher coefficient for the clip model for the core categories. And in this case, you will be showing mostly results from the clip model, and all others models will be buried a bit. And vice versa, if you're searching for some tools which doesn't have proper images, but good description, then in this case, you can bury results from the clip model and higher up all other systems. By playing with these numbers, you can get very efficient results and very good results from all these three retrieval systems. And let's summarize a bit. For the last year, neural search went from experimental phase to the production phase. We see that many companies actually bringing neural search into production systems and using it on daily basis. We see that this area is getting improved, and we have new models and new approaches coming up almost every month. And text to image is now the real thing which we can use. And there are lots of retailers that will be extremely happy to see these models in their catalog, because they have good product images but bad description. So in these cases, it will be most helpful to use this type of models. And we see the approach that companies getting neural search into their search systems, not by switching to this completely, but by gradually increasing the percentage of involvement from this type of image, of this type of systems. And thank you so much for listening, and I wish all of you the happy searching.
Happy searching. Thank you very much.